Now we are using the Gauge model to obtain the estimated conditional variance and conditional returns based on the historical observation of our raw data. So in this part, so previously we are assuming that the epsilon t, this epsilon is following a normal distribution, isn't it? Now we're going to use another parametric distribution, which is student t distribution. It just happened to the return series most probably will follow. It's a symmetrically distributed data set, so therefore normal and student t actually provide this characteristic. And of course, student t might be um, more suitable or appropriate to handle the extreme values in the financial data. Okay, so we have using the AR GACH11 normal distributed residual or shocks. Now we're going to move to a student t distribution. So basically the way to calculate the value is almost the same, okay? Just that okay, so here we have we're going to have so we're going to have a same almost the same model. So use blue color. So we have AR1, and so this is the combination of ARIMA and GACH. Okay? So this is 1 student T. Okay. So how are we going to estimate the value? So the code here, the MATLAB code is everything is almost the same, just that in the ARIMA specification here, we're going to have we're going to use the distribution. So we need to specify the distribution. Okay, distribution. Then it should be T. It should be T. Or you can just go to the ARIMA. Let's say. So you can use the documentation and find out the possible specification. Okay. So for this one, maybe we can just use the Gauge model. Okay. So in this case, you can see distribution. If by default is Gaussian, okay. If not, let's say I think they should have okay. So this basically is all. So this one is student T. So therefore you have a distribution and student T. Then you can fix the degree of freedom. Of course, if you put it in this way, then the numerical methods will actually estimate the degree of freedom for your student T distribution. So here I think they are more general. Okay, this is all the possible the so-called, so the epsilon T also can be named as the innovation process. Let me check. So this one I think distribution. So here I think you can choose. So these are all the distribution. I think you can find out beside the normal and student T, there are all types of distribution you can fit into your model. But somehow the most common method should be the common distribution in student T and normal, because they are both symmetrical, and student T can capture under the low degree of freedom, able to capture the extreme values in the financial data. Okay, so we just change this to student T. That's one student T. Okay, so this is the additional code. You just specify this. So the rest is all the same. The rest is all the same. But this one also you need to change, because for student T, you need to find out the degree of freedom first. Okay, degree of freedom. Okay, so after that we can just run and have a look. This one I need to change because this is a Z value, okay, 5% or plus minus. Okay, so student T, first you need to know the degree of freedom, then you can determine the uh, the value of the T values, okay, of the T value. So here we just run it. Then you can see the estimated result. We somehow have the degree of freedom estimation. Okay, so you see there's a degree of freedom which is 7.52. Okay, so most of the financial data, the degree of freedom is from 3 to 6. So this is considered, yeah, of course it's heavier, it should be heavier than normal distribution, but it's less severe. Most of it 3 to 6 is considered quite um the 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 intent, I mean the tail behavior of the tail actually can extend to a smaller value or larger value. Okay, so the coefficients value, the rest of it might be close to what we have found in a normal distribution. So you can just look at the, okay, for example, this one, AR1 is 1.1442. So previously, if you look at your estimation here is 0.13816. Okay, so under the the student T assumption 0.144. Okay, this one previously is 0.138. There's a slight difference between a normal and student T. So you just write down the possible equation for it based on this result. Okay, so the degree of freedom is 7528. Or we can just run and have a look at it one more time and have a look at it. But definitely this is not the correct one. Okay, so let's say this is the set of data we have. But somehow previously I run it and then end up to have a different set of data. Okay, but the degree of freedom I get is 8.3525. Okay? Maybe I'm not sure whether I fix this value or not. But basically it will based on the AR1 model is based on this. The GASH11 student T will based on this. Okay, these coefficients. So the forecasted value, the same thing, the returns 0.0019 for the previous data. Now for student T is 0.0017. Okay, there's a slight difference. So for variance, 2.7347 compared to the forecasted value is 2.57. So it's quite close. Okay? It's quite close. Okay, so let's say the data set we have, we just write down the values. Okay, so here let's say we have a RT estimated result. RT equal to 0.000954. Okay, let's say this is our result, 0.1387. So this is our AR1. AR1. So the GASH11, so this is close to 0, e power minus 6, close to 0. So this is for alpha 1, 95254, epsilon t minus 1 squared. So for epsilon, and for beta 1, close to 0.9, 1 sigma t minus 1 squared. Okay, so this is our estimated result. And then we have the degree of freedom. So just now we see 7.5, isn't it? So somehow in the previous run I get 8.3525. So this is the degree of freedom, right, for student T distribution. So the estimated value minus 0.0017, isn't it, just now? Compared to 0.19. So for student T here is 0.0019, normal. This is student T, 0.00, so it's quite close to it. So for the variance, one step ahead, 2.66 times 663. So if you run in your PC, you might end up to have a value close to this 10 power minus. Okay, so if I want to find out the 5% quanta, so quanta basically is the in terms of probability lah. So if you talk about VAR, you must multiply the capital. Okay, let's say the $100,000 on it. So this is student T. So with the degree of freedom 8.3525. So this is equivalent to the T value 0.05 is minus 1.8595. So for normal, this now is 1. This is sorry. This is 1. The Z value is 1.64, is it? So for student T is 1.85. So 5% basically you need to do a standardization for this T value, okay? So standardization for student T is this T value 1.8595 divided by the degree of freedom over, so this is basically the degree of freedom 8.3525 over 8.3525 minus 2. Okay, and then this will give us a value 1.6217. So you can see compared to 1.64, this is slightly less than 1.6449. Right? So this is less than. This is basically smaller than the in terms of magnitude. Right? So the impact actually will be less than. This is a larger value basically, isn't it? In terms of negative, in terms of magnitude. So minus 1.64 is larger than this. So then we can find out the 5% quanta. So this is a 5% quanta student T degree of freedom. Okay? So this one, basically you're going to get the forecasted value minus 0.0017 minus 1.6217, then times the estimated standard deviation. Okay, so you have 2.6663 10 power minus. Okay, so end up you're going to get 0.024 minus 78. So in terms of VAR, 5% or 5% VAR, you can say this is 100K times minus 0.024. So end up the loss will be $2,470. Okay. So this is for the 5% VAR compared to, you see, this is a 5% VAR. 5% VAR under the student T assumption, 2,400. But if you look at the VAR for normally distributed, is 2827. Okay, this is 2478. Okay, so this is less than the. I mean, this is the loss is less than. So basically, student T in this case have no impact, or actually is actually the VAR is less than the normally assumption data. Okay, but somehow if you increase the confidence level, then let's say you want to find a 1% VAR. Okay, you do the same thing, but the impact of the student T will be more. Okay, in this case because this is 99%. Okay, So this will be 100,000 times. So this value after the multiplication is minus 0.04295. Okay, so in this case, the loss will be 4295. And this value, as you can see, is smaller than the 3,539. Okay, so the conclusion, we can say that for student T assumption, the value at risk, let's say, so you can also find out the 2.5%. This is 1%, 2.5%, maybe you can compare. I think 2.5% will be quite similar between the student T and normal assumption. Okay, but somehow if 1%, then you can see the impact of the heavy tail can be seen 4,300 compared to 3,500. Okay, so the impact of student T was seen under the very low percentage. Okay guys, so this is basically our analysis to determine the value at risk using the gauge method. So you need to estimate the gauge coefficients. After that, you need to do the forecasting, one step ahead, two steps ahead, depends on how far ahead you want to forecast. Okay, so for let's say 2 days or 3 days or 10 days ahead forecast, you just need to multiply the square root of time t. Okay, let's say square root of 10 days ahead, square root of 10 to the var you get, then that will be the 10 days ahead forecast. Okay, for the var. Okay, so we have shown two different values, and we see the conclusion we get is for 5% var, the normal assumption actually end up to have a higher value at risk as compared to student T. But somehow when the percentage go down to 1%, the var for student T is much higher, which is 4,300 compared to 3,500 for the normality assumption. Okay guys, so this will be our session for estimating the or forecast the value at risk 1 day ahead using the gauge method under two models. First one is normal assumption, second one is student T assumption. Okay guys, so see you guys again, bye bye.